So the next complex we will take it as a neutral complex, NiCO4 times, that is nickel tetracarbonyl, very famous complex, student. Just keep it in mind, this is very significant. Again, this complex has been targeted in many of the competitive examination. Nickel tetracarbonyl, oxidation state of the nickel is 0. Don't confuse, it is not a D8 system. It is not a D8 system because what happens is, electronic configuration we are writing as 3D8-4s2 for the nickel will be writing 3D8-4s2. Since carbonyl is a very strong ligand, what happens is it's a neutral ligand, it will make this electron to jump here and get paired. So initial electronic configuration will be, try understanding 1, 2, 3, 4, 5, I am talking about the d orbital, right? This is the initial electronic configuration, and 4s orbital you have 2 electrons. What happens is the strength of the ligand is so high that these 2 electrons will be pumped here and make these electrons to pair and get converted into 0. That is so that the d orbital will be fully filled, which is stable. That means the s orbital is the empty, whereas d orbital is fully filled. So the electronic configuration of the nickel in this complex is 3D10 4s2, 3D10 4s2, not 3D8 4s2. It is 3D10 4s0, not 3D8 4s2. Hence, it is not a D8 system, it is a D10 system. So, what is your prediction regarding the geometry of this complex? Straight away you can say it is a tetrahedral. Don't confuse. See, you have many times you may be confusing. That is, you have a nickel and strong ligand, you may be thinking it is a square planar, not so, only D8 system, it is not a D8 system, nickel plus 2 is D8, not the nickel 0. So tetrahedral complex, hybridization is sp3, take a look here, see most of the cases the tetrahedral complex will be paramagnetic, but this is a diamagnetic complex. Why it is a diamagnetic complex? Because it is a 3D10, D10 configuration, whatever may be the nature of the filling, you will be having always ending up with a pairing. That is, all the 5d orbital will be filled here. That is, you have E and T2. E comes first as far as the tetrahedral is considered. E4, T2, 6. This is the electronic configuration of nickel tetracarbonyl. E4, T2, 6. CFSE will be 0. CFSE will be 0 because this is fully filled, this is also fully filled. So CFSE is 0. So magnetic property, very important. Magnetic property is, it is diamagnetic. It's diamagnetic. It is diamagnetic, or magnetic moment, if at all they are asking magnetic moment, it's 0, magnetic moment is 0. How about the stability? It is highly stable because complex containing strong ligands are making stable complexes. So it's a highly stable complex, it's a D10 system, tetrahedral complex, sp3 hybridization, E4T26, CFSE 0, magnetic property diamagnetic, magnetic moment is 0. Very, very important, students, just keep this in mind. Just keep this in mind. Okay, so this we have done, nickel tetracarbonyl. We'll take few more complexes. That is, for example, I will take manganese complex, MnBr 4 times, this is -2, so I can write it as K2MnBr, right, that is K2Br. What is the oxidation state of manganese? +2, you have Mn +2, so D5 system. What kind of complex it is? Straight away you can write it as tetrahedral because it is not a D8 system, there is no chance of getting the square planar complex. Hybridization is sp3, right, that is electronic configuration will be, what is the electronic configuration? D5 ET2, right, that is E will be 2, right, T2 will be 3, right, E will be 2, T2 will be 3 because delta naught is less than the pairing energy. Delta naught is less than the pairing energy, right, it goes up rather than getting paired. E2, T2, 3, CFSE will be, what is the CFSE value for this particular complex? CFSE will be 2 into minus 0.4 delta naught plus 3 into minus not minus 0.4 minus 0.6 delta naught, 3 into plus 0.4 delta naught. That means it is CFSE 0 or CFSE is 0 for this complex. This is a less stable complex. Less stable complex. Very clear? It's a less stable complex. So we have done with the electronic configuration. So magnetic property. If you look at the magnetic property, you will observe this is how E orbital will be filled, T2 orbital will be like this. It is paramagnetic. Number of unpaired electrons, it's 5. So magnetic moment will be square root of n into n plus 2, that is square root of 5 into 5 plus 2, that is, this is 35 is the value we are getting, right? 7 into 5, 35, that is near to 6, that means 5.89 Bohr magneton, approximately 5.89 Bohr magneton. Right? So this is about this particular complex. Likewise, we can predict for any complex for that matter. It could be octahedral, it could be tetrahedral, it could be square planar. We have covered all the cases, students. Application part of the, the crystal field theory. In the case of octahedral complex, we have outer orbital, inner orbital complexes and all there, low spin, high spin. In this case also low spin, high spin complexes are there, but there is no question of the outer orbital, inner orbital complex. So this is about the applications of the crystal field theory.